Hi everyone, this is Matt Whitbread. This is my presentation for the final assignment that we had with Predictive Analytics for our dengue fever forecasting exercise. So it was an interesting one, a little disappointing in terms of the results I got, but nevertheless. So I'll start with a couple of visuals. I don't have many because I struggled, to be honest with you, to find really any compelling visuals to share, really put together to help me with this. So this is all the San Juan data. I used the larger data set, the one that went back to 1990, as opposed to the other one that was only back to 2000. But the number of cases shown up top, you can see that there's obviously a number of spikes. There's a clear seasonality within this, which is shown below. Again, seasonal being weekly, but one first half of the year, very low average amount of cases, and then it starts to increase pretty significantly with a lot of variation within the number of cases. So there's certainly seasonality within this. What I thought was interesting about this data set was it provided the meteorological, i.e., weather variables along with the cases, which in my mind I thought was pretty key to trying to figure this out and try to predict it, because not just from the other papers and research that I pulled up on other mosquito-borne illnesses like dealing with malaria and so forth, but just intuitively it made sense in terms of if this is a disease that's spread by mosquitoes, then the more mosquitoes, the more potential cases you might have. So I thought that the weather variables would be really key to looking at this. So I focused a lot of my time and analysis on that, and I showed two the variables within here. And I isolated these two because I end up using them in one of the models that I'll talk about before. But it also shows a high degree of seasonality, but also a very consistent pattern. So this is minimum air temperature and specific humidity. So I looked at all the weather variables, and not all of them had much seasonality. Some of them are relatively flat, like average temperatures. Precipitation really moved around quite a bit, although I did use that because I felt compelled to use it. But these two stood out in terms of having a very clear, sharp, defined component of seasonality within this. The other interesting thing about this is if you compare this pattern here to the seasonality in the cases, there's a clear lag in terms of when you start to see, let's for example, a specific humidity starts to pick up. It isn't until about 8 weeks later you start to see a pickup in terms of the number of cases. So again, this made sense to me because I thought from a mosquito's perspective, they have to have a life cycle. They have to have standing water, a minimum temperatures can't be below, I think, 17 degrees Celsius. So there should be pretty unique conditions in terms of letting or allowing mosquitoes to be hatched, to be born, and become prevalent enough where they can start really pushing out this disease and so forth. So I also used that within a model, although again, not with a whole lot of luck. So that's kind of it in terms of the visuals that I have. I'll discuss my approach in terms of how I built the models and ultimately kind of settled on what I settled on. So I started with three models, each starting with very simple from STL, moving to a bit more complex with ARIMA, then to neural networks. So I wanted to get at least three models in terms of difference in complexities, but that ARIMA model was something that I really wanted to focus on because it allowed me to implement, or I should say, incorporate the variables that I was looking to try to capture. So this is using the full data set. So this is the very top table here. This is using the full data set on the San Juan data. And interestingly enough, we can see that the neural networks based upon the root mean squared error significantly outperforms STL as well as ARIMA. So I thought that was quite promising initially, but interestingly enough, down in this second table here, this is using a training set and a test set. So I used the first 13 years of the San Juan data as the training set, and then the remaining 5 as the test set. And I did that for the purposes of another model that I'll discuss in a second. But a couple things jump out at me. First, the neural networks, it does absolutely terribly. So it does very well in terms of the full data, in sample data, but out of sample it just gets killed. So basically dismissed neural networks from this initial model here. What I did also is I built a seasonal ARIMA with external regressors. This is where I tried to pull in the other variables into the model to try to see if they would help with some explanatory power within this. And interestingly enough, from the root mean squared error perspective, you see an improvement within this over just a seasonal ARIMA of 27, so 24 to 27. So not a huge improvement, but at least an improvement in terms of accuracy, which I was happy with. I then took a step forward and tried to implement this with lags. So what I did is I basically pulled the cases back 8 weeks to try to line up the seasonality of the cases with the seasonality of the weather variables that I was looking at, hoping that that would allow the model to essentially use the variables to capture the variability and the errors with more accuracy. So that was my intent, and it took me a while. And unfortunately, it ended up really manifesting in a very minimal improvement whatsoever. So you can see the 24.4 of the non-lagged model versus the 24.36 of the lagged model. So, a lot of effort for really nothing. And apparently, I was just on the wrong path. But nevertheless, at the end of the day, I decided that the CRMAX or the seasonal ARIMA external regressive model was the right one to go forward with. So in order to do that, I had to predict forward the three external exogenous variables that I was using, which is humidity, minimum air temperature, and precipitation. So I put them through the same process looking at these three models and evaluated. And as it turns out, that neural networks ended up being the best model, at least 2 out of 3, and came in second within the precipitation. So that's how I built the model. I created neural networks to forecast the next 5 years worth of external exogenous variables, and then I used a seasonal ARIMA model with those external, or I should say, exogenous variables that were forecasted in order to generate my forecast for the cases for the next 5 years. And unfortunately, this ended up yielding, I think, a 26.8% mean absolute error. So that was even worse than the benchmark example that they gave me. So this was not the best in terms of performance. But I think if I was to continue playing with this, I would still look for ways to link those variables to the cases in some way. But for now, that's kind of basically what the model ended up with. So it was a good one and a good semester. So thanks everyone, and it was great working with you.